Hello again, students. So for this video we are going to start to look at weak acids and bases and how they differ fundamentally from the strong acids and bases we talked about in the last video. Let's go ahead and get started. Now, the idea of a weak acid and base is just that it has a K expression that is much less than 1. So they only become partially ionized in water. We have to assume that the majority of our reactant remains and only a small fraction of it gets turned into hydronium and the conjugate base. Now, one of the things we must get used to is writing a generic equation, because it doesn't matter what the anion is. All weak acids essentially follow this expression, that the idea that some protonated anion undergoes a dissociation to form H plus and A minus, the anion, the negative anion. So the anion is one less charge than it was previously, one more negative than it was previously, whatever that anion was. So we can write this for any acid, and we will constantly use just this generic form so we don't have to write a new one each time. And then the expression, the Ka expression, the equilibrium expression, which is products over reactants, is that our two products, hydronium or H plus and the conjugate base A minus, all over our starting material HA. We do not need to include water because water is a pure liquid. Since this follows for any acid acting like an acid, we specifically refer to this as a K sub A, Ka. This Ka expression is the equilibrium constant for the dissociation of an acid in water. We can treat it the same regardless of what the acid is. So there will be a variety of different Kas that have been already determined for us. It tells us how strong or how weak the acid is relative to others. We can do a similar situation with a base. We can set up a K subscript B or Kb expression. That a generic base, upon mixing with water, will become protonated and form hydroxide. The Kb is for the base, so hydroxide. However, we're just saying a generic B, and the B has accepted a proton. So the conjugate acid of that base. Now, alternatively, it's easier, instead of saying B and BH plus, to look at the conjugate base of that weak acid we talked about in the last slide. That A minus is capable of doing the same thing as our standard base. And so we don't have to have a new situation. We don't have to learn new variables. We can just say that A minus, in presence of neutral water, will accept a proton to reform its weak acid and form hydroxide. And so we can have a Kb in terms of just A minus and HA instead of having to get new variables. Now, with that in mind, the size of our Ka and our Kb will relate to the relative strength of our acids and bases. The larger the K, the closer that K is to 1 or greater, the stronger the acid or base. Most of these Kas will be expressed as 10 to the negative something power. So when that negative power gets smaller, it is getting closer to 1. Reminder, strong acids and strong bases usually have a K that is much greater than 1, like 100 or 1,000 or even greater than that. And while these Ka and Kb expressions hold true for neutral water, please note, in the presence of a strong acid or strong base, they will still completely react. That the presence of hydroxide will completely depronate HF. And then we can reestablish a new equilibrium expression. But the first things first is all the pure hydroxide must be consumed. So, now there's a direct relationship of Ka and Kb, because remember we said an acid strength directly relates to its conjugate base strength. So looking at a generic acid, HA and A-, we can relate their acid strength and base strength, and that for a generic reaction, Ka equals H plus A minus over HA, and Kb being HA and A minus over OH minus. If we were to multiply Ka and Kb together, the HAs and the A minuses would cancel out. And if they were to cancel out, you would be left with just H plus and OH minus. So we can directly relate the Ka to the Kb through Kw, similar to the H plus and the OH minus. So the stronger the acid, the weaker the conjugate base. And the stronger the base, the weaker the conjugate acid, because as one of these gets bigger, the other must get smaller. We can also give what's called a pKa and a pKb. However, a pKa and pKb is simply the negative logarithm, the negative power function of the Ka. And same with the Kb. So with that in mind, we can also say that 14 equals the pKa plus the pKb. It's a lot easier to deal with, but it can be done. There's a lot of interlinking relationships here. Now, when determining the pH of a weak acid, one of the key problems here is with a strong acid, we can simply say the hydronium was equal to the concentration of our starting material because there was complete dissociation. But with a weak acid or weak base, there will only be partial dissociation, so we will not have the full amounts of H plus and A minus that you would expect. And so how do we go about calculating the pH for these situations? Now, we will set up an ice table, but once you get the hang of it, the ice table is no longer necessary. We might have to set up a quadratic equation, but there's other ways around that. But the idea is we need to consider this equilibrium expression. This is a situation where, much like in chapter 15, we will know how much starting material we have, but we will not know what is all the concentrations at equilibrium. So the idea here, remember, is that when we're setting up our equation, the idea is that at equilibrium, Q equals K. But at the initial starting point, Q is going to be 0. We're going to say we have essentially no A minus and very little amounts of H plus. So if we're calculating the pH of a 1 molar weak acid, you can write an initial situation where HA is 1 and the concentration of H plus and A minus is 0. So because Q needs to approach K, some amount of that HA must dissociate and form equal quantities of H plus and A minus. So at equilibrium, some amount of HA will have dissociated, X, and some amount of H plus and A minus will have formed, which is X and X. And so we'll have this. So Plugging these values into our Ka expression, we can then solve for x. Now please note the concentration of H plus and A minus are the same. And so multiplying them together would give us an x squared value. Unless we are told otherwise, we're going to assume that H plus and A minus are the same. And that will make our calculations easier. Well, so we plugged them in. So we have Ka equals x times x over 1 minus x. Now, here's where it could be difficult. If Ka is known, and hopefully Ka is known, and Ka is significantly small, much smaller than the concentration of our initial acid, no quadratic is needed because we're going to make one key assumption. That if HA concentration is divided by the Ka is 400 times or more, that means the amount of dissociation of the initial acid is so small that it becomes a rounding error. If we subtract 1/1,000,000th from 1, you won't notice it in your calculator when you do the calculation. If you subtract 1/10th from 1, you will notice it. But if the amount of acid that dissociates is small enough, it will play a part on the pH, but it will not play a part in the concentration of HA left. So, for example, if Ka is 10 to the negative fifth, so calculating our relationship of HA over Ka, we get a number that is 100,000, which is much larger than 400. So this is a pretty safe assumption. So we'll set this up. We have a Ka, we have 1 minus x simplifies to 1. We cross multiply, and so we get x squared is equal to 10 to the negative fifth. When we square root that to get x by itself, we get x is a concentration of 3.2 times 10 to the negative third. So 0.0032. Now, that is the concentration of H plus, and it's the concentration of A minus. Taking the negative log of that would give us the pH, and so we have a pH of 2.49. Now, if I try this again with our new x and try to resolve for the x squared, we get the same value again. This only will work if x is significantly small enough. Plugging this in and solving will give you the same value. Now, rounding the sig figs way down here will have changed ever so slightly, but not enough that it will make a difference. Now, God help us if the concentration is low. Suddenly this matters. So if the concentration is instead 0.00015, we try to calculate that and the difference is only 15, so it's less than 400. Let's see what effect that would have. So that's where we have to set up a quadratic. Real quick, a quadratic looks like this. So for a generic equation, ax squared plus bx plus c equals 0, quadratic looks like negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Well, setting up the equation, Ka equals x squared over HA minus x, what you end up having to do is you'll multiply HA minus x to the other side, and you'll get Ka times HA, and you'll get Ka times x, and that's equal to x squared. Now, getting everything to the other side, so this equals 0, you'll have x squared, equals 0, plus Kax minus Ka times our HA. So this is our C, and this is our B. So with that in mind, plugging these values in, you have negative Ka plus or minus the square root of Ka squared minus 4 Ka times HA over 2. So that's a generic equation we could use if we know these two values. Now, obviously, you have to check the positive and the negative values, because one of these values is either going to, one answer, x equals, you're either going to get a negative number, which is wrong because you cannot have a negative concentration, or you're going to get x is greater than HA, which is also wrong, because HA minus x cannot be less than 0. Cannot be less than 0. So there's only going to be one value that will ever make sense. The other ones are wrong. So you can do that. It is possible with the quadratic. It is a pain in the butt. You could plug these numbers in and plot it on a graphing calculator and find the zeros. That is another way to do it. I will eventually show you a shortcut method. So as you see in this situation, I've already solved this one for us. You can see that I've run the quadratic and essentially gotten our value, and got 3.4 times 10 to the negative fifth. And when I take the negative logarithm of that, I get a pH of 4.47. Relatively straightforward right there. Now, the shortcut is what I call the iterative approximation. It makes a big assumption that gets the first value kind of wrong, but then we use the kind of wrong value to get closer and closer approximations. And so by doing this, we can get the correct answer. So the first step is we assume that HA minus x is significantly small. If it is small enough, we can safely ignore the HA minus x. But if it isn't, we'll see it when in the iterative approach. So we say HA minus x is just HA. And let's solve for our x squared. Once we solve for our x squared, it's a matter of turning that x squared into an x. So we do it the first time, and we get an x of 3.9 times 10 to the negative fifth. If we do that negative log of that, we get a pH of 4.41. Maybe it's not significant enough to really matter to you, but to some people it may be. And as Ka and HA approach in similar sizes, the changes will be more significant. Now, with that in mind, we take that x and we plug it into our equation for the HA minus x. So we figure out how much the HA will have dissociated by based on that first problem, and resolve for our x squared. And once we resolve for our x squared, we find our new x. So we did it after the first time. We get 3.3 times 10 to the negative fifth. A significantly different number, which the negative log of that would give you 4.48. Now, most times that might be good enough to stop, but we could keep going, and it changes again to 3.4 times 10 to the negative fifth, or the pH of 4.47. So after 2 iterations is now the same value as our quadratic. So we can do this just doing the same thing over and over again and slowly get it closer and closer to the quadratic without having to set up and solve a complicated quadratic each time. So it is a shortcut, and I'll show that in practice in a little bit. Now, with that in mind, our acids and bases can be classified into 3 categories, which is how we're going to mathematically treat them. We could have very strong acids, very weak acids, or moderately weak. Now, very strong, the Ka is very big. We don't have to do a lot of calculations because the initial starting concentration of our acid will be equal to our H+. On very weak acids, our Ka is so small that the dissociation of our initial concentration of acid is insignificant. And so it just becomes the square root of Ka times the initial concentration of acid. But when we're in the moderately weak category, where the Ka is similar in strength to the Ha, we need the quadratic or some sort of iterative approach to try to give us our value, try to give us our concentration of hydronium. But once we have that, in all 3 steps, we still have to take the negative log, because more often than not, we want the pH, not just the H+. So keep that in mind. Now, the same situations can be true for bases. We can have strong bases, very weak bases, and only moderately weak bases. And we'll have to have the same approach. Now, with that in mind, let's go on some examples. Our first situation is pH of 0.35 molar boric acid with a Ka of 5.8 times 10 to the negative 10th. So, in order to do this, let's go to the DocCam. If we want to see, okay, do I need the quadratic? Would say 0.35. Do I need the iterative approach? 5.8 times 10 to the negative 10th. Yeah, this is going to be much, much greater than 400, I can tell you right now. And so we do not need the iterative approach. We do not need the quadratic. We can set up an ice table, but largely speaking, all of the ice tables end up something like this. Ka over x squared, Ha minus x, and since this is very weak, it's just going to be x squared over Ha. And since this is weak, we're going to say 5.8 times 10 to the negative 10th. And we're going to multiply this by 0.35. 0.35. And that's going to be equal to our x squared. So let's do that. 5.8 times 10 root negative 10 times 0.35, and that's going to be equal to x squared. So that's 2.03 times 10 to the negative 10th. We got to square root that, because that will give us x, and x is equal to our H+. So when we square root that, so I hit the square root that, we get 1.4 times 10 to the 10 to the negative fifth. And then the negative log of 1.4 times 10 to the negative fifth is simply we 4.85. There's our pH. That's our pH, 4.85. Pretty simple. Well, no, it's not. I'm lying. It's not simple, but it is absolutely doable if we take a slow approach. Once with practice, this will become simple because it's always done the same way. Now, in this case, we have we will need to do the quadratic, or we could take an iterative approach. We have 0.13 molar hydrofluoric acid, 6.8 times 10 to the negative fourth Ka. So I'm going to show the iterative approach instead on that. I'm going to show it on Excel. So let's see. We have 0.13 molar. So HA is 0.13 and our Ka is 6.8 E negative 4. Let's double check we need the quadratic, and that's just equals this number divided by this number. 191 is not greater than 400. So we need a quadratic or some sort of iterative approach. So remember, we're going to say x squared over HA equals Ka. So the iterative approach is going to be first, what's HA minus x? Then we're going to take the next thing, which is going to be HA minus x. Put that HA minus x times Ka. And then we're going to take that number. We're going to say the square root of HA minus x Ka. And that's going to be equal to the x. So our first one, 0.13. Okay, well, then we're going to say, what's our Ka? So Ka times this. Now, specifically, I'm going to do something special. I'm going to make sure it's always going to be the same number. So I'm going to type a $ into here and a $ into here. Actually, no, not there. I don't want that one. I want always E3. So $. When you type a $ into before a letter or a number, it is telling Excel to always use that box. Always use something from column E and box 3. And so whatever formulas come afterwards, we're always using that one. And now it square equals SQRT parentheses this square root of this answer. And so I'm going to put that into scientific so we can see the number better. So 9.4 times 10 to the negative third. With that in mind, I'm going to say equals this minus that. Okay? So now my concentration has dropped from 0.13 to 0.121. Now, with that in mind, I'm going to drop that equation down. And so now my multiplication has now become, instead of 8.84, it's 8.2. Because now it's referring to, you can see the blue box there, it's still the same box, but now it's referring to this box as our HA minus X. And I'm going to drag this equation down. And it's changed from 9.4 to 906. Well, I'm going to drag this guy down again, and our number dropped from, so now it's, okay. No, that one's not quite right. So this should have been, I'm going to make sure always use, always G, always 6. With that in mind, when I drag that formula down, now if I take this out to more significant figures, you'll be able to see there is a difference. But right now, you cannot. There's a slight difference here. And if I drag that down, you'll see, okay, this is slightly different. Drag that down, that's slightly different. So it's really, each time it's getting further and further and closer to the actual number. So with that in mind, I don't have to do this more than one. At this point, this guy is more than close enough. This answer is more than close enough. It's not going to change. Now I take the negative equals negative log 10 of this value, and I'm going to have our pH. So if I do it the first time, I get 202. Essentially 203. Then I get 204, 204. It's essentially 204. By doing this, I can get the exact number exactly with relative ease. However, it does take a little bit of knowledge about Excel in order to do this. You cannot just wing it entirely. You have to be able to understand a little bit about Excel first. Now, with that in mind, let's get back. Let's go. So we could have done the quadratic at any time and got the same number. So 906, so 204. This last one I think will fit under, it's a base, which makes it a little trickier. But 0.42, we want the pH of a base that has a KB of 1.7 times 10 to the negative 9. How do we know it's a base? I've given you a KB value. That is probably the easiest way to figure out, oh, I should probably do it as a base. You may not recognize the term pyridine, but the KB says it's a base. So we have a KB is equal to x squared over essentially base. And x is going to be equal to OH minus. Well, 0.42 divided by 1.7 times 10 to the negative 9th is definitely going to be much, much greater than 400. So we can ignore that, do the iterative approach. We don't have to do the iterative approach. We can just say that that is a safe rounding error. 1.7 times 10 to the negative 9th equals x squared over 0.42. Let's solve for x squared. So 1.7 times 10 root negative 9 times 0.42. That gives us 7.14 times 10 to the negative 10th equals x squared. We square root both sides, we're going to get our x. Our x is, of course, going to be 2.7 times 10 to the negative 5th. If I take the negative log of that, 7 times 10 to the negative 5th, this is going to give us POH. So we can still take the negative log and make our lives easier. But remember, that is POH. So 4.57 is not my answer, because pH is going to be 14 minus my 4.57. 14 minus my pOH. So 14 minus 4.57 is going to give us a pH of 9.43. Clearly, it's going to be basic. And that is what we see in that. So, that in mind. Let's get back. And that's what we're going to see. 9.43. Remember, a base should have a pH greater than 7. Well, that's where we're going to stop for today. We're going to look at some of the stranger aspects and some of the more theoretical things about acids and bases for that last video. Have a good day.